I'm Sean Lovejoy, the new chair of the Nonlinear Focus Group, replacing in the program Sergil Sharma, who's now the ex-chair. And it's my pleasure this morning to introduce first the chair of the Lorenz the Lorenz Lecture Committee, John Rundle. And just before I do that, I wanted to make one little comment about the Nonlinear Focus Group, which is that we really would like as many people as possible to affiliate with our section. That builds the section up. And often people don't pay so much attention to where they tick boxes and things when it's time to affiliate. You can be a secondary member as well if you feel that's more accurate. But anyway, please support us that way.
Thank you, Sean. Well, it's my great pleasure this morning to introduce Daniel Schertzer. He prepared at Ecole Polytechnique and Ecole de Ponts in France. His PhD was at the Universite de Pierre et Marie Curie. Pardon my French here. He did his research has done his research at the Nice Observatory, the National Center for Meteorological Research at McGill, at the Dynamical Meteorological Lab at CNRS, at Clemson, and he's now at the Ecole de Ponts. His research has been focused on a number of important topics over the years which have deeply influenced many people in many areas. And his focus has been on understanding and analyzing and modeling a nonlinear variability of geophysical and environmental fields. He's used renormalization techniques in turbulence. He's looked at the role of non-local interactions, which are important not only from atmospheric and hydrologic problems, but also in solid earth problems. He's been very influential on his analysis of intermittency and multifractals. He's worked for many years with Sean Lovejoy, also, who's a close colleague. He's published 2 books, 2 monographs, and well over 100 papers. And it's my great pleasure today to introduce Daniel, who will be speaking about predictability and uncertainties in geophysics. So, Daniel.
Okay, thank you, John, for this very nice introduction. I will try to manage this computer. Oops. Yes. Okay, that will be the only animation of this talk because I lost the movies and so on. So, anyway, do this. I could not miss the opportunity to say a few words about Lorenz, who passed away on the 16th of last April. And I think the obituary of New York Times was a good summary. He was at the same time a meteorologist, and he was presumably the father of deterministic chaos. His landmark paper of 1963 was indeed published in the Journal of Atmospheric Sciences, and the title was Deterministic Non-Periodic Flow, and it had been so much influential that every domain of science were influenced by this paper. After that, there was a second paper where he started to develop a rather simple image of what deterministic chaos would mean, and it was about the flap of a seagull which could which could forever change the future course of the weather. This was based on a discussion he had with meteorologists, by the way. And after that, it became the question of the flap of a butterfly's wings in Brazil and so on. And that was the last image which was so well known that we are still speaking about butterfly effect. Of course, all the detail of this achievement can be found in the book, for example, of John Gleick about chaos making a new science. And the title, I think, is really summarizing rather well what was involved. It's a kind of new science. There is a good summary about this achievement for the citation of the Kyoto Prize for Basic Science, where it's said that it was one of the most dramatic change, in mankind's view of nature since Isaac Newton. Okay, he got a lot of medals recognizing this achievement, and in particular he got the first AGU Roger Revell Medal in 1992. However, what is less known is his contribution to fields which were not restricted to deterministic chaos. And today I will spend some time about that. It's in particular the case of his paper published in TELUS, where he was addressing the question of predictability for systems having many scales of motion. And in fact, doing that, he concludes this paper with some ironic remarks about the solution of paradoxal aspect of the butterfly effect or the seagull effect, if you like. So this lecture will be developed to the relationship between complexity in time, more or less the paper of 63, and complexity in time and space, based on the idea developed in the paper of 69. And, of course, their implication. So when we are speaking about prediction, there is a remark of Lorenz which is particularly true. He remarked that methodologists have often underestimated the mathematical difficulties of prediction. And this is partially due to the fact that we are, all of us, under high pressure to solve the problem instead of understanding the problem. Prediction is not something so much common for mankind. It's rather recent in a given time, in a given way, because for a long period it was really not the business of man, but the business of God. So to say in advance means prediction, but in fact there are three different types of prediction which were emphasized by Lorenz. The first kind is starting with initial condition, that's the so-called Cauchy problem. The second kind is when there are change in boundary condition, Neumann problem, and unfortunately most of the practical problems are a mixture of two of these conditions. So thinking about prediction, the history is a bit complex because at the beginning mankind was very slow to find a way to make prediction. At the beginning it was just based on geometry, as perfect as possible. And finally, we reached a level of dynamics and gravity and differential calculus, numerical method with the Euler method, which was developed in 1768. And all these recent successes led to kind of overestimate of our abilities to predict. So that, for instance, there is a very well-known sentence of Laplace considering that everything is computable, in fact. But 50 years later, a series of problems were discovered. First, there was a problem of ill-posed versus well-posed problems by Adama, and this has indeed practical implications for geophysics. For example, if you look at the book of Dimri about inversion, this is nicely emphasized. Of course, the Newtonian revolution, we discovered, in fact, we were not able to solve the free-body problem, which is still an open problem. Also, there are some exact solutions now which have been obtained. So, in fact, we were a bit more modest, and especially Poincaré pointed out that there are good lessons to be known by methodologists about that. And in fact, his sentence is really about the question of non-periodic flows as the title of the paper of Lorenz in a way. And there we arrive to the butterfly effect. So I just want to show a very simple example of that. For example, this is just the Lorenz model, the XZ projection, taking 100,000 points, which are initially uniformly distributed in a small circle. And you can see at the beginning that the motion of the points is not so impressive. They rather stay close together. And step by step, there is some dispersion. And suddenly, about the time 19, there is a big spreading all over a kind of strange attractor. So this is very impressive, and so impressive that it became a landmark for science. In fact, this has been a bit generalized by different equations of this type, finite nonlinear differential equation, or iteration map. There's an equivalent with Poincaré section about that. And what is behind is better understood now with the help of the so-called multiplicative ergodic theorem, MET, developed from the work of Lyapunov and especially by Osseldetz, and which just shows that under rather mild conditions, you have an exponential growth of the dispersion due to you just need a kind of ergodic measure and a finiteness of the log of the Jacobian. This is an illustration for the Lorenz model. So for intermediate time, we have result about the fact that there is a Liouville equation, which is just a continuity equation for the ergodic measure in the phase space. So finally, we have a full image of what could happen, and this is an illustration given by Palmer, and which has been used a lot to understand what could happen in our prediction system. So there are four steps. First step, which is initial. After that, a small deformation, which is rather linear. Second step, where there is some nonlinear deformation, but not too much. And finally, a total loss of predictability. In fact, the story is a bit more complex than that. You can look in the detail in the structure of the attractor by looking, for example, to the eigenvalue of the Jacobian matrix. It's a bit already not so trivial. And for application, you have to do much more because you don't have so many points. Sorry, I skip it. Usually, you are making ensemble realization with 50 simulation. And so you want to be as effective as possible. So there have been a lot of development about techniques to do it as efficient as possible. So I will skip it, this kind of example by Van Itsen and Nicolis about another model, the lower order model of atmospheric model, which has some interesting feature. I don't have time to develop, but with some link with regime and blockings. And there's been also the idea to use nonlinear propagator in order to estimate more efficiently the dispersion of points. Now we are not only doing ensemble simulation, but also ensemble assimilation. And this become a routine now in different weather services. And finally, what is more recent is a problem of hydrological forecast using also kind of ensemble techniques. So that a lot has been done in this direction. However, what is behind that, we are not addressing, in fact, complexity in time only. We are addressing models which are, in fact, complex in space. And there are differences with it. So usually it's introduced with partial differential equation. A very classical example is a Navier-Stokes equation plus an advection dispersion equation for a passive scalar, such as temperature or whatever. And unfortunately, there is no straightforward mathematical extension of what we learned from complexity in time to complexity in time and space. So we have to look for something else. And Lorenz started to do it in 1969 in a paper which is somewhat complex to read. And here there is this famous figure which has been used a lot to explain that there is a maximum predictability time of the order of 5 days. So the basic ingredient was to look at the transfer of energy from correlated energy to decorrelated energy. And of course, I have trouble with it. Okay. Okay, so it was starting with a small, okay, this is a spectrum. Okay, it's not exactly in log plot, but almost. And, okay, the small scale are on the right. They correspond to large wave numbers. The large scale correspond to low wave number on the left-hand side. And it's starting from about meters down to up to 40,000 kilometers. And you have the whole spectrum is preserved, but step by step, the division between correlated energy, which is on the left, and decorrelated energy, the borderline between the two is moving with this vertical line. So it's starting with a time step of 15 minutes, after that 1 hour, 5 hours, 1 day, 5 days. Okay, the problem, in fact, we are discussing about turbulence, so we are really addressing Navier-Stokes equation with all its non-linearities, complexities, and so on. And Lorenz used, in fact, a closure. He defined himself a closure. It was very close to a quasi-normal closure. He knows that there are problems with quasi-normal closure, but at the time, it was almost the only thing which was available. This analysis, after that, has been refined by Lees and Kretnan using more sophisticated closure model, the test field model, which is a kind of phenomenological modification of the direct interaction model, which has direct link to the Navier-Stokes equation. After that, it was revised once again with EDQNM, with evident quasi-normal model by Mete and Lussier in 1986. All these simulations agree to the idea that the borderline between correlated energy and decorrelated energy was moving upward in a power law. In the case of the two last models, it was really a power law of the type 3.5. What can I say? Yeah. I want to show that this result can be obtained by simple scaling argument. And this is based on the fact that, in fact, in turbulence, it's usual to introduce a kind of local time for a given size L of eddies. It will be just the size of the eddy divided by the shear, the velocity shear of this eddy. And therefore, if you consider that there is a flux of energy, epsilon, which is more or less constant through the different scale, you have another equation which gives you that simply this flux will be u squared divided by this time, tau. Okay, here it was t, but it was in fact tau of L. And you obtain this kind of equation, u to the power of 3 should scale like L, in fact, because there is a constancy. That's the hypothesis of Kolmogorov 41. So if you are finishing the reasoning is that simply the Lyapunov exponent is just the inverse of a characteristic time, should be the inverse of this characteristic time of the eddies, the time of destruction of these eddies. So finally, you obtain this kind of equation for the Lyapunov exponent. So the Lyapunov exponent strongly depends on the scale L, and furthermore with an exponent which is negative. So it means that when you are going to smaller and smaller scale, there is divergence of this Lyapunov exponent. So it means you don't satisfy any longer what was discussed about the time complex system, about their uncertainties. So there is something really new is the fact that this borderline between correlation of two realization and their decorrelation is moving with a power law. That was a new feature put forward by Lorenz in '69. If you want to do a little bit better, you have to think about Navier-Stokes equation. And the problem of Navier-Stokes equations, they are strongly nonlinear. The mathematical properties of their solution are still unknown. It's still an open question for mathematicians. And, but on the contrary, there is something simple There are scale symmetries which have been known for a given time, and especially exploited by Sedov. The idea is very simple. If you rescale the distances x by lambda, factor lambda, and then you have to rescale all the different variables or fields by different power of this ratio of scale lambda. And there are simple linear relationship between these exponents. So in fact, the idea is that there is a strong symmetry inside of the Navier-Stokes equation, even though we don't know exactly what is going on with this equation. This is rather formal, so it doesn't help too much at the beginning. And finally, the way to understand it a bit more was done with the help of cascade, an idea which is coming back to Richardson, 1922, and which just explains that we can understand the dynamics of the atmosphere by the idea that you have large structures which are breaking down in smaller structure, transferring their energy, and so on, down to the viscous scale. And here the viscous scale is the order of 1 millimeter. In fact, Richardson was not only a theoretician, he did some experiment about that. He used data at that time, and he showed the first kind of qualitative law of turbulence, that there is a scaling viscosity over a wide range of scale from centimeter up to 10,000 kilometers. And that was the first scaling law discovered in turbulence. And, okay, but this idea after that was in fact, okay, so after that this idea was developed in two models. It took some time to do it. The first one who did really it was Yaglom in 1966, and after that Mandelbrot in 1974. So just using this idea of cascade, you can start with a cube having a given level of energy, and you are randomly distributing this level of energy in smaller subcubes. Yeah, sorry, I'm speaking about cubes, just squares, in fact, for it's a two-dimensional figures. The vertical axis corresponds to the energy. And the way to distribute the energy is just by using multipliers, independent multipliers for each of the sub-eddies. As soon as you have done that for one step, you can do it again for another step, and so on and so on. The surprising fact, this is a very simple model at first glance, but it has a lot of non-trivial properties. And finally, at the beginning, we thought that there will be a simple way to understand it using fractal geometry, saying more or less, you are concentrating the bulk of energy on the fractal set. But in fact, it turned out that generically, the figure is much more complex than that. You have, in fact, going to very smaller scale, a lot of differences between the different eddies. Some have a very high energy, some have very low energy. And these differences is going higher and higher when you are going to smaller and smaller scale. So in fact, it corresponds to the notion of multifractal. In fact, to understand this field, it's not only a fractal set, but a series of a hierarchy of infinite number of fractal sets, each of them corresponding to a given level of energy when you are going to smaller and smaller scale. Another problem about Navier-Stokes equation was what is the dimension of the motion? Should we consider that the atmospheric motion are more or less two-dimensional or three-dimensional? And there have been a lot of arguments about the fact that large scale should be two-dimensional because the aspect ratio is very small. On the contrary, three-dimensional for less, say, more or less human scale. And at the beginning, there was kind of empirical support about that, the Van der Hoeven wind spectrum, which gives you the idea that there were two peaks of energy, one for quasi-three-dimensional energy, two-dimensional large-scale energy, and between them, a mesoscale gap. That was very comfortable for the development of dynamical metallurgy. People were concentrating on that, and considering there was no contamination from the three-dimensional motion up to the large scale. In fact, there were other rather opposed point of view in different textbooks. For example, a very classical one, it's a series from Atkinson, adapted from Olansky, and here it's kind of a Strommel diagram, where on the top you are putting in log-log on log-log the duration of a given structure, on the vertical the size of this structure, and corresponding to that you can put in this table the different animals that you can find, meteorological animals you can find from microscale turbulence up to baroclinic waves. The surprising fact is that, in fact, all these different phenomena are in a log-log plot more or less distributed on a straight line. And the slope of this straight line corresponds once again to this kind of relationship between time and space. So in agreement with Richardson and Kolmogorov, three-dimensional like turbulence. Okay. Of course, this is just a kind of first glance about the possibilities. I must insist that if you had a kind of two-dimensional turbulence, you will have a kind of constant time life for eddies, and it will be along the vertical. It's not at all observed. Okay, to do that, to better understand that, you cannot use vertical sounding with the help of meteorological balloons. You can combine them with horizontal fly of airplane flights, and also you can use vertical sounding with LIDAR, airborne LIDAR. So this level 4.5 kilometers is the level of the airplane, and the LIDAR is pointing downwards, and the reflectance of the LIDAR gives you more or less the concentration of the aerosol. If you are zooming on this kind of structure, again, you find smaller scale, but this time the orientation is rather vertical instead of being rather horizontal like it was for large scale. You can use also drop zone in order to analyze the atmosphere, and once again at different level you can look at the wind shear and see if you have a kind of Kolmogorov or Bogdanov-Bukov and so on, different type. Finally, all these data seem to indicate that you have just to give up with the idea of having kind of isotropic turbulence, so that the property will be the same along the vertical and the horizontal. And if it was true, then the distance to be used to measure different things will be just the usual Euclidean distance. It seems, on the contrary, you have two different behavior along the vertical and the horizontal. And finally, the way to reconcile them is just to use an unusual metric, which is defined by a kind of iso contour giving the same wind shear. And in that case, instead of having this kind of isotropic scale, you have a kind of anisotropic scale, which is based on ellipsoid rather than on spheres. Okay, another problem about turbulence, atmospheric turbulence, is what could be the outer scale of turbulence. Should it be limited to 10 kilometers? If it was isotropic, it would be of this order. If it's anisotropic, how far you have to go, how large could be, the scale could be contaminated by kind of three-dimensional turbulence. And to analyze that, you can first use one radar based on ground, but you are limited in scale. You can go from 1 kilometer to 128 kilometers. Nevertheless, if you are taking the different moments and plotting them in a log plot, you can see first that they are giving straight line, which is in agreement with scaling, and furthermore, there is an intersection point going very far to 30,000 kilometers. And this intersection will correspond to the lowest variability of your field. So these kind of extrapolations seem to indicate that you can expect that turbulence could go very far, up to very large scale. To check that, you can use first satellite images of clouds, and you are doing the same job, but this time you are observing scale which are much larger, up to a few thousand of kilometers. You can do that also for rainfall measurement with the help of the TRIMM satellite, which has a complex trajectory. And along all this trajectory, you can compute different statistical moments of the difference of rainfall according to a different distance. And once again, you obtain this kind of more or less straight line for different value of the exponent q, the different statistical moments. Again, there is kind of intersection to large scale of the order of the Earth. So finally, the answer seems to be to use cascades which are not isotropic but anisotropic up to very large scale. And in fact, there is a scheme to show that it's not so difficult to change from isotropic to anisotropic cascade. You can do it a bit more sophisticatedly using the notion of generalized scale invariance. The idea is just to formalize the idea that you can go from one structure to the other one by taking an intermediate step. So you create a kind of multiplicative group. And then you have a generator and all that. As soon as you have these tools, you can simulate not only isotropic clouds, but strongly anisotropic clouds. I'm sorry for the movies, they don't work. Now, as soon as you have all these tools, you can revisit what was done by Lorenz, Lees, and Krecknan. And the first thing we did with Marsan at the time was to use just one simulation and to look at the decorrelation between different points. Lorenz showed that there is some connection between that instead of using two realizations of the same field. What we observed at the time that indeed the decorrelation between in space of this kind of simulation was really happening with bursts, not in a regular manner, a kind of Gaussian way, like it would happen in the case of the closures which has been used by Lorenz, Lees, and Krecknan. But you can do a step more and do exactly the same as they did, but with cascade. So in fact, you are taking two realizations, one cascade A, one cascade B, and at the beginning, you consider they are just decorated at very small scale, and step by step, you can see that the range of scale where they are created is just decreasing, and in a power law. Okay, that's the basic idea. And after that, all the mathematics are working very well. You can compute the law at which this ratio of scale where the two cascades are strongly dependent is decreasing. You can do a lot of things because, for example, if you are looking to the correlation between the two cascades, as they are multiplicative processes, their multiplication is just a new multifractal field, but with the specificity that it has only a range of scale which is decreasing with time. So this can be simulated rather easily. This kind of example of that, we have two realizations, A and B here. We are starting with the same path for A and B, and then when we are arriving at time t0, we are just making it dependent, the subgenerator of this cascade. So that's a technical aspect. That's a small, that's the way you are generating by fractional differential equation your cascade. And as soon as you are making that independent, step by step, you are decorating the smaller scale. And this can be seen here, step by step, the two cascades A and B are becoming more and more independent. The third realization is a bit different. Instead of keeping on introducing some agitation at small scale, you are deciding to kill the agitation. So you are just preserving the flux of energy, but in a deterministic manner. And that would correspond to a kind of deterministic subgrid modeling of your cascade, of your field. In that case, you can see very quickly that you are losing the complexity of the field. In fact, just these images give you some ideas about two consequences. The first is that the decorrelation between the two processes A and B is rather slow, and it's in fact associated to poor load divergence, not exponential load divergence. And therefore, there is some irrelevance with finite dimensional scenario of the Liouville equation plus the multiplicative ergodic theorem. They do not work on these kind of processes. Second is that, as we saw, there is a drastic difference with third realization. There is a loss of variability, which is rather fast, and it corresponds to the fact that practitioners now are very convinced that you have to use, in fact, stochastic subgrid modeling to keep a good variability of your field. So now, most of the weather forecast models now are using stochastic subgrid modeling, whereas for decades, they were working to get the best deterministic subgrid modeling. Okay, last part I want to speak is about the question of climate change, and more generally about change of climate, not necessarily due to only mankind. Anyway, so I agree with Paul Crutzen and Evgen Stormer about the fact that for the last 2 centuries at least, the role of mankind has been so important that we can speak about Anthropocene for this geological period. And if we want to explore it, we can start with the idea that, for example, we have some data, then we have some model equation. We can discretize them on the Earth. We can compute that with the help of large computer, get data, and once again compare that, the output of the model with the real data, and improve and so on. However, the output is rather complex to explore, and furthermore, there are some limitations. For example, the general circulation model have usually a resolution of the order of 200 kilometers. This is particularly insufficient for rainfall, and therefore you have to, if you want to speak about the hydrological extreme, you have to find a way to guess what could be the fluctuation in the future of your rainfall. Because rainfall over a square of 200 kilometers by 200 kilometers is not really rainfall for an hydrologist. And so there are different ways to do that. But one way is to use, once again, the idea of cascade, like being the way to understand the physics of Navier-Stokes equation. And to do that, in fact, you can use multifractals, especially a type of multifractal which are called universal multifractal, because, in fact, they are defined by only 2 exponents, and they are attractive for other multifractal processes. So it's a kind of generalization of the what's the name of that? Sorry, the Gaussian attraction for most of the additive processes. Here you are using a kind of extension for multiplicative processes. Okay, these 2 exponents are in fact have some rather simple signification. The first one, I would take the simplest one, is a codimension. It's the dimension of the space minus the dimension where the fluctuations are concentrated. The bulk of fluctuation are concentrated. So it's called the mean intermittency codimension. It corresponds to a measure how inhomogeneous is the mean field, your mean field. On the contrary, alpha, the multifractality index, measure how this intermittency will vary when you will look to different level of activity. Okay, the first interesting fact is that if alpha and C1 are both increasing, then the extreme will increase. It's rather easy to show. And on the contrary, if they're decreasing, okay, both of them, the extreme will decrease. So when you are computing these indexes, parameters, on the climate scenario from 1860 to 2100, and with different resolutions, so you can see there are resolutions from the straight line, of course, corresponds to the full period, so 240, and after that for 40 years, 25 years, and 10 years. And you can see at the beginning that alpha is more or less stable, and then start to decrease. And you have exactly the opposite behavior for C1. So the first consequence of this kind of analysis is that it could explain the present difficulty to analyze the evolution of hydrological extreme in a climate scenario. There are a lot of different papers with opposite point of view about this question. And this is not surprising if you are looking to this opposed effect of the mean intermittency and the decrease of multifractality. So in order to guess what is really going on, you have to make a refined analysis. And this is a way to do it is to use a notion of kind of maximal probability which could be found in a given sample. And this is computable from these two first parameters, alpha and C1. And you can see that this gamma S has indeed fluctuation, but not so much. And it seems there is a kind of trend indicating that the model indicate that there should be an increase of precipitation. On the contrary, if you are just checking what is going on with the maximum of the precipitation, you can see that much more wide precipitation. So you cannot guess so much by using just this precipitation, the global precipitation. So to conclude, to finish, I want just to point out there are new development in the direction of what is called now random dynamical system. I have not so much time to explain what it is, but it's kind of generalization of stochastic modeling, but with combining a dynamical system approach. And for example, Gill and collaborators claim that it could be the solution to understand and reduce the uncertainty about climate change instead of using simply deterministic model. So I'm just in time for my conclusion, a bit late maybe. Well, the first set of conclusion, I think anyone will agree that the chaos revolution demonstrated that first, geophysics are not only applied sciences. They are still facing fundamental problems, starting, for example, with the Navier-Stokes equation. To have fundamental problems doesn't mean that we have to be too modest and to stay alone. On the contrary, when these problems are well advertised to the entire scientific community, we can get global responses which help us to get new tools. And also not only new tools, but new practices. A good example of that, about new practices, the weather forecast hydrology fully changed due to the butterfly effect. For 40 years, anyone was trying to have the best prediction. Now it's over, anyone is trying to have at least ensemble prediction. If possible, probabilistic prediction. Okay, nevertheless, I pointed out that there are huge differences between what was inside of the paper of 63 and the paper of 69, and new development in that. And we have to be careful about that. First, there is a relative space-time symmetry as soon as you have a space-time system. You have no characteristic time of predictability, and you have, in fact, polar decays instead of exponential decays. It's in a way good news. It means that the predictability limits are much higher than we could have thought. However, frequently our practical skills are below, much below than these theoretical predictability limits. Stressed by, for example, by Lorenz in '85, we need, in fact, a much more precise knowledge of the atmospheric condition and dynamics. I pointed out all the debates about the long debate which has been held on the question of the mesoscale gap, and it's clear that it's still a question which should be solved in order to know exactly how to play the game to make prediction. So that means that we have to urgently implement new concepts and methodologies, including in the Ensemble prediction system, in particular to exploit the scaling properties between time and space. Last point is that there could be an interesting prospect now with the appearance of a convergence between kind of dynamic system approach and stochastic modeling, for example, with the help of random dynamic system. Concrete output of that could be a dynamical stochastic forecast.
Okay, we have some time for questions.
I just want to support your statement about the space-time complexity that from our experience in hydrology we see when you go, things are space-time and the problems are really require new tools, development. So I'm looking at my friend's work in seismology, the space-time. So maybe there's a need to understand what are the big questions in some of the fields and what is being done in that area. Do you have any thoughts on that?
Maybe you can repeat the question.
Well, I should repeat the question.
Yes.
Well, to summarize it, Vijay insisted about the question of space and time and the necessity also to work on this question and, in fact, in an interdisciplinary manner because, in fact, it's all the disciplines of geophysics are concerned. He mentioned, of course, hydrology, but seismology. I mentioned myself atmospheric sciences, but I think all of them are concerned. Of course, we can agree about that, and I think that's important. There is, in fact, there is an NG section now in Multifractal focus group in AGU to help these cross-disciplinary exchanges.
Daniel, I have a question. What do you think about the information theoretic approach to complex systems? In what ways can traditional sort of linear measures versus perhaps things like Salis entropy enter into these problems?
Well, I didn't want to introduce this complex debate about the different measures of complexity. And in fact, there are quite different approaches. Some of them are, for example, based on the idea that everything is computable. Okay, there is, for example, the Kolmogorov entropy and different things like that. I would like just to point out that there are indeed some relationship, for example, with the question of hierarchy of dimension which intervene in the multifractal processes. These are maybe more concrete. They just measure where there is some activity of your field, which a given level. And that's kind of information. So there are some formal equivalents.
Any other questions?
What's your opinion on the use of highly precision to simulate nature? Don't you think it's more useful to use highly precision than exact precision to modelize and simulate natural phenomena?
Well, I'm not so sure I understood your question. You are speaking about finite precision and...
Yeah, because you are speaking about simulation and computation.
Yeah.
What do you think should be more appropriate? Is it exact precision or highly precision?
Well, except the problem of exact precision with computers is unsolved problem. So, indeed, but in any case, we have first to understand the physics of the problem and to see what would be the appropriate way to cope with it. However, one thing which was emphasized by Lorenz himself was the fact that one bad news of all this question of predictability is that measuring with finer and finer resolution doesn't give you a better prediction. And that was a point he stressed oppositely to previous work done by Charney and Thomson, who on the contrary tried to argue that you have to have a better network in order to have better prediction. In fact, this question of predictability shows that there is some limitation on that. I don't want to say that we are not to improve the measurement, but unfortunately, when you are looking to a time lead, then you have a problem. You don't get so much by finer and finer resolution. So in a way, I believe it's part of the answer. We will have always to cope with finite precision and always to know that this finite precision is introducing some unpredictability, but at the same time inside of a global complex problem of complexity, which in any case will introduce uncertainty.
One more question?
Well, I briefly showed some results about that. I have no time to discuss them. The work by Talleyrand co-workers is exactly on that. Yeah. So that's a problem to introduce indeed the notion of ensemble, not only in the simulation when you are going forward, but also in the data assimilation where you are in fact going backward. So in fact, there are new developments in this direction to use more and more this idea of ensemble. So in fact, uncertainties. So once again, it's stressed that some ideas which were really a bit weird 40 years ago became usual daily practices of meteorologists now.
Okay, thank you, Danielle. I think Sean has some presentations to make now.
Just wanted to present a certificate on behalf of the Nonlinear Focus Group for the Lorenz lecture. Danielle. Thank you.
Yeah, I don't want to say too much because I think it's just important there have been some recognition of different works which have been done with many people. And I just want to go a slide ahead. And maybe it's not very clear, but it's a remembrance of, well, some time ago in 1983, we were with Sean and other people, Uriel Frisch and Michael Gill, discussing a lot about the mesoscale gap. The discussion was not always very soft. It was a kind of hot debate from time to time, but it's useful. And what I remember at the time, Lorenz raised his hand and politely asked to say something, and he just said what is written here, that more you average wind spectra, more you obtain Kolmogorov spectrum. and that make a kind of peace agreement.
We now are going to have a talk by the Donald Turcotte lecturer, I guess, or what's the, it's just an award, okay, the Donald Turcotte Award, excuse me, which goes to Irina I Rypina. And this award is given for an outstanding young scientist, and she will give us, I think, a 20-minute presentation, or till 15 or 20 minutes. Let me see. So here's your...
Thank you very much.
And, your talk should be here, yes.
Excuse me, how do I put it in on the bottom? The research I will talk about today was done together with Professor Mike Brown and Hossein Kochuk from University of Miami, and together with Larry Pratt and Ilya Vdovichenko from Hole Oceanographic Institution. This research is concerned with transport in an idealized three-gyre system with application to the Adriatic Sea, and we have used a dynamical systems approach in our studies. Before going further, I would like to briefly discuss the problem under investigation. The picture shown here is a spaghetti diagram of 201 surface drifter tracks which were deployed in the Adriatic Sea during 1990s, during approximately 10-year period of time. The main feature of this plot is a robust multiple gyre pattern. Drifters are seen to sometimes get trapped within each of the gyres for a long time, but also many examples of drifters moving from gyre to gyre are also seen. This suggests the following question: what controls inter-gyre transport in a perturbed three-gyre system? This question will be the central topic of my talk today. The two-gyre system has previously been studied and is fairly well understood. I will show in this talk that in the three-gyre system, a new phenomenon arises which is not present in the two-gyre system. The dynamical systems approach to transport is based on two related types of ideas: the Kolmogorov-Arnold-Moser theory and the manifold structure. Before proceeding, I want to mention a few papers. The first paper provides a good introduction and overview of dynamical systems approach to transport in oceanic flows. It has a strong emphasis on the manifold structure related ideas. The second paper explains transport in an idealized three-gyre system with an application to the Adriatic Sea. This is the topic I will focus on today. It uses both types of ideas, the Kolmogorov-Arnold-Moser theory and the manifold structure. The third paper here explains some theoretical results which are related to the strong KAM stability phenomenon. I will use these results later in my talk. And the last two papers discuss some applications of the Kolmogorov-Arnold-Moser theory to zonal jets in planetary atmospheres. And the focus is made on the role of these jets as transport barriers. I will not have time today to discuss the content of these two papers, except to say that they are related to my talk. The outline, my talk will be organized as follows. I will start with the discussion of the mean surface circulation in the Adriatic Sea. I will use two different models. One will be observationally based and one will be a simple analytical model. Then I will give a short review of relevant results from dynamical systems theory and then move on to the discussion of the behavior of the three-gyre system under time-dependent perturbation. First, I will use an analytical model and then I will move on to the fully observationally based model. Conclusions will be given at the end. This, as I said before, in our studies we have used two different models for the Adriatic Sea. One was observationally based, one was a simple analytical model. The plot on top shows contour levels of the stream function, observationally based stream function, which describes mean surface circulation in the Adriatic Sea. The domain of the Adriatic here was rotated counterclockwise by approximately 45 degrees, and a no-flow condition through the Strait of Otranto was superimposed to make the domain closed. The middle picture shows contour levels of a simple analytical stream function. Despite of its simplicity, it has all the necessary features for our studies. It also has correct length and time scales. The main features of the three-gyre geometry are shown on the lower subplot. The three-gyre geometry implies existence of 5 stagnation or stationary points, 3 of the elliptic type associated with the core of each gyre, and 2 of the hyperbolic type, which separate gyres from one another. Associated with each of the 2 hyperbolic points is a homoclinic trajectory. The 2 homoclinic trajectories form 2 8 figures, one embedded inside the eastern loop of the other. Because of our focus on surface transport, it's natural to assume that the flow is two-dimensional. Together with an incompressibility assumption, this allows one to introduce a stream function psi, so that Lagrangian equations of motion have Hamiltonian form, with the stream function playing the role of the Hamiltonian. We will further assume that the stream function can be separated into the mean, steady flow, and the time-dependent perturbation. Now I will introduce action angle variables, which we will need later for the Kolmogorov-Arnold-Moser theory discussion. For any steady stream function psi 0, it's possible to introduce a pair of variables I action and theta angle in such a way that the Hamiltonian is only a function of action. Lagrangian equations of motion in terms of I and theta still have their Hamiltonian form, and they are written below. We can see that these equations in terms of I and theta can be easily integrated to give that I is equal to constant following each trajectory, and the conjugate coordinate theta increases linearly in time from its initial value theta 0. It's convenient to define theta in such a way that it increases by 2 pi after each complete period of motion. Then omega is just the frequency of motion on a particular trajectory. So, in terms of action angle, action is an unperturbed trajectory label, motion is periodic with period 2 pi over omega, and the quantity omega prime is a measure of shear. This quantity, shear, will be very important in later discussion. The steady problem is completely integrable. It means trajectories coincide with streamlines. It means that all trajectories are regular curves and no chaotic motion occurs in such a system. However, when the system is perturbed by time-dependent perturbation, then trajectories are no longer constrained to fall on top of streamlines, and some trajectories may become chaotic. An important question is whether all trajectories will be chaotic in such system, or there will still be some regular trajectories in the system. The answer to this question is given by the Kolmogorov-Arnold-Moser theory. According to the KM theorem, when a steady stream function psi 0 is subjected to certain classes of time-dependent perturbations, some regular trajectories, or more correctly tori in high-dimensional phase space, will survive in the perturbed system. This is important because each surviving torus provides an impenetrable barrier for transport. The CAM theorem is formulated for a general class of multi-periodic perturbations. Note that this is not a simple periodic perturbation. This is a much more general class. But it is important to remember also that there is no CAM theory for general time dependence. It means that CAM theory-related results should be applied with some care. The other two conditions which are required by the KM theorem are the Diophantine condition and the non-degeneracy condition. The Diophantine condition requires that surviving tori should be sufficiently non-resonant, and the non-degeneracy condition in its simplest form requires that resonances are isolated. The version of the KM theorem which is listed here is important for two reasons. First, it is formulated for a multi-periodic class of perturbations, and second, it requires a less restrictive non-degeneracy condition. In this form, the KM theorem was recently, last year, proved by CEREVE. The mechanism by which regular trajectories become chaotic is due to excitation of resonances. Resonances are excited when the frequency of motion on a trajectory is rationally related to the forcing frequency of the perturbation. Because omega is generally a function of action, infinitely many resonances are excited by fixed value of the perturbation frequency. Among those, however, low-order resonances are the most important. When a resonance is excited with a particular trajectory, then this trajectory breaks down and becomes chaotic. But also, some neighboring trajectories will be affected by the resonance. Resonance width is a measure of the distance from the resonant trajectory within which other trajectories are affected by the resonance. It is intuitively clear that when two resonances are excited far away from each other and they have small resonance widths, the two resonances will not overlap and the intervening trajectories will not be affected by either of these resonances. However, when two resonances are excited close to each other and they have large resonance widths, the two resonances will overlap and all intervening trajectories will become chaotic. That's why resonance width is an important parameter. One of the definitions of chaos, so-called Chirikov's criterion of chaos, is based on overlapping resonances. Now we will use resonance width to explain the basics of the strong KM stability phenomenon. A simple analysis reveals that the non-degenerate resonance widths scale like omega prime to the power 1/2. Recall that omega prime is a measure of shear. It means that low values of shear are generally associated with small resonance widths. It means that resonances in these regions are less likely to overlap and intervening tori or regular trajectories are more likely to survive. Each surviving torus provides a barrier to transport. So we expect to see barriers to transport in regions which are associated with small values of shear. It will be shown that in the three-gyre system there is a shearless trajectory. According to the strong KM stability phenomenon, we expect to see barriers to transport in the vicinity of this special trajectory, at least for small perturbation strands. This is the end of the overview of dynamical systems techniques, and now I will move on to the analysis of the three-gyre system. The upper two subplots show contour levels of the observationally based stream function and the analytical stream function. The two lower subplots show a period of trajectory as a function of its initial position for trajectories that start from black dots shown on the upper pictures. Comparison from left to right shows that there is a very good agreement between our analytical model and the observationally based model. Second, we can see three regions of qualitatively different behavior on each of the two lower subplots. These are trajectories trapped within the right-hand side gyre, trajectories that go around two gyres, and trajectories which go around all three gyres. The jumps in T correspond to two homoclinic trajectories, two figure 8s. Between the two homoclinic trajectories, T has local minimum. Now I will use action angle variables to show that there is a shearless trajectory in the three-gyre system. For trajectories that start between the two homoclinic trajectories, plots of T period, omega frequency and omega prime shear as a function of action are shown below. We can see that consistent with the previous graph, T has local minimum, omega has local maximum, and omega prime has a zero crossing. Recall that omega prime is a measure of shear. It means that between the two homoclinic trajectories, there is a shearless trajectory. Due to the strong cam stability phenomenon, this trajectory is very resistant to breaking. It means that we expect to see barriers for transport in the vicinity of this trajectory. This shearless trajectory is shown by green line over here. Now I will show some simulations to check whether our predictions are true. To simulate a time-dependent three-gyre system, we have used a perturbation which consists of a superposition of standing waves. When frequencies of standing waves are commensurable, the perturbation is a periodic function of time. For periodic perturbations, we can construct a Poincare section. Poincare section is a technique that allows to view trajectories in periodically perturbed systems. To construct a Poincare section, one needs to sample a trajectory after integer multiples of perturbation period. On the Poincare section, regular trajectories appear as discretely sampled smooth curves, and chaotic trajectories appear as sets of dots that fill area. For the analytical system, two Poincare sections are shown on this slide for small value of the perturbation on top and for large value of the perturbation on the bottom. For small value of the perturbation, we can see two figure-8 shaped chaotic regions. One is shown in red, one is shown in black. These two figure-8 shaped chaotic regions do not overlap, and they are separated from each other by a green curve. This green curve corresponds to a surviving regular trajectory in the vicinity of the shearless trajectory. And again, it is present due to the strong cam stability phenomenon. However, the stability of the shearless trajectory is not absolute. It will break down when the perturbation is too large. And this is what happens on the lower plot. The transport barrier in the vicinity of the shearless trajectory is broken, and one large chaotic region is formed, which includes portions of all three gyres. Under these conditions, there is transport between all three gyres. So, to summarize quickly, the behavior of the three-gyre system under perturbation is qualitatively different for small and for large perturbation. For small perturbation, there is a transport barrier of the strong cam stability type in the vicinity of the shearless trajectory. This transport barrier prevents mixing between the western gyre and the rest of the system. For large perturbation, this transport barrier is broken and transport between all three gyres occurs. Now I want to change emphasis from the cam theory to the manifold structure. Transport of fluids is controlled by special material curves of fluid, which are called stable and unstable manifolds of hyperbolic trajectories. Stable and unstable manifolds for the three-gyre system are shown schematically here by lines of different colors, red and pink for unstable manifolds and blue and light blue for stable. Stable and unstable manifolds are material curves. It means that neighboring fluid particles cannot cross them. Now I want to comment about the importance of manifold intersections and to define a lobe. The intersection between the manifolds is called homoclinic if it is produced by stable and unstable manifolds which emanate from the same hyperbolic trajectory. The intersection is called heteroclinic if it is produced by stable and unstable manifolds that emanate from different hyperbolic trajectories. Domains of fluid which are trapped between intersecting stable and unstable manifolds are called lobes. Lobes are important because fluid which is initially located inside the lobe is constrained to move with the lobe as the flow evolves. For the three-gyre system, there are two hyperbolic trajectories which separate adjacent gyres from each other. For a time-independent steady flow, which is shown on top, the two hyperbolic trajectories are stationary, and the associated stable and unstable manifolds coincide with each other, forming two homoclinic trajectories. These two homoclinic trajectories form two figure-8s, one embedded inside of the other. Between the two, there is a shearless trajectory, which is shown in green. When this system is perturbed by small perturbation, which is shown on the middle subplot, The two hyperbolic trajectories are no longer stationary, and stable and unstable manifolds do not coincide with each other but intersect transversely. For small value of the perturbation, a transport barrier of the strong chem stability type is present in the vicinity of the shearless trajectory. It separates two chaotic regions from each other. Transport within each chaotic region is governed by homoclinic intersections of manifolds. So under these conditions, a transport barrier is present and all manifold intersections are of the homoclinic type. For large perturbation, the transport barrier in the vicinity of the shearless trajectory is broken. One large chaotic region is formed, and under these conditions, there are both homoclinic and heteroclinic intersections of manifolds. So, for example, the dark blue curve intersects both the pink curve and the red curve. This is a schematic diagram showing qualitatively different behavior of the three-gyre system under perturbation. Now I will show some simulated manifolds to check whether this behavior holds or not. For an analytical time-dependent three-gyre system, manifolds are shown on this plot for small value of the perturbation on top and for large value of the perturbation on the bottom. And we see that qualitatively this is the same behavior that we saw in the schematic diagram. For small value of the perturbation, only homoclinic intersections of manifolds are present. This suggests that there is a transport barrier of the strong chem stability type which separates the western gyre from the rest of the system. For large perturbation, we see that both homoclinic and heteroclinic intersections of manifolds are present. This corresponds to the case when the transport barrier is broken and there is a fluid exchange between all three gyres. Now I will introduce a fully observationally based model. Our fully observationally based model of the Adriatic Sea consists of a steady observationally based background and an altimetric perturbation superimposed on top of it. Because we know both this background and the perturbation, we can study the dependence of the perturbation strength, epsilon. In our studies, epsilon is equal to 1 corresponds to the full or true altimetric perturbation. This slide shows a comparison between simulated surface drifter tracks and measured surface drifter tracks. And we can see that our observationally based model does a pretty good job to show qualitative behavior of the surface drifters. Because the altimetric perturbation is not a periodic function of time, we cannot construct Poincare section. However, we can still construct manifolds, and we can still check whether there is a qualitative change in the manifold structure for small and large perturbation strengths. This is what was done here. The manifolds for the observationally based model for two values of the perturbation, small on the left and large on the right, are shown on this plot. The four upper subplots are finite time Lyapunov exponents. I don't have time today to discuss what they are, except to say that they measure a local separation rate between fluid particles. And the ridges or red curves in the four upper subplots correspond to stable and unstable manifolds respectively. The manifolds are also shown by lines of different colors on the two lower subplots. Now I want to focus on the two subplots a little more. We can see that for small value of the perturbation, all manifold intersections are of the homoclinic type. This suggests that a transport barrier of the strong chem stability type is present, which separates the western gyre from the rest of the system. For large perturbation, we can see that both heteroclinic and homoclinic intersections are present. This suggests that the transport barrier is broken and transport between all three gyres occurs. The transport between all three gyres is governed by heteroclinic lobes, and now I will show the evolution of the heteroclinic lobe in forward and backward time. The evolution is shown here, so that in forward time we can see that this heteroclinic lobe is pulled towards the western hyperbolic point, a segment of unstable manifold increases and the segment of stable manifold shrinks. In backward time, it's pulled toward the eastern hyperbolic point. The segment of stable manifold increases in length, and the segment of unstable manifold shrinks dramatically. In this motion, the area inside the lobe is conserved. This is a consequence of two-dimensional compressible flow. And this is the last simulation I would like to show. It shows the evolution of two sets of initial conditions. One is shown in red, one is shown in blue, for two values of the perturbation, small above and large below. For small perturbation, we can see that each set of initial conditions is well steered, but there is no mixing between the two. This corresponds to the case when a transport barrier is present. For large perturbation, we can see a large amount of mixing between the two. This corresponds to the case when a transport barrier is broken. So the conclusions from my talk are listed here. We saw that a transport is qualitatively different for small and large perturbation. For small perturbation, a transport barrier of the strong chem stability type isolates central and eastern gyres from the western gyre, and all manifold intersections are of the homoclinic type. For large perturbation, the transport barrier is broken. Both homoclinic and heteroclinic intersections are present, and it is the presence of heteroclinic intersections that makes gyre to gyre transport possible. And the last remark is that this last observation suggests that generally non-local transport in multi-gyre systems is governed by heteroclinic intersections of manifolds. Thank you for your attention.
We have time for one or two questions. Any questions for? Maybe I can ask you something. I think you said you had 201 trajectories that you'd use to test this. This is, it seems to me this should be a small number for what you need. Is this, or is it? Well, what's your feeling about that?
Well, these are all trajectories that were available, and they were deployed during 10-year period in the Adriatic Sea. And I use these trajectories to get the mean surface flow. And I feel that it's, of course, the more trajectories, the better. But I feel that these 201 tracks do a pretty good job in estimating the mean surface flow.
Yes.
In the dynamical systems approach, we have two related types of ideas. One is based on Kolmogorov-Arnold-Moser theory and the strong chem stability phenomenon, which leads to the presence of the barrier. The second type of ideas are stable intersections of stable and unstable manifolds. These two are related. So what is shown on this slide is that when a transport barrier is present, all the manifold intersections are of homoclinic type. These two ideas are related. If the transport barrier is present, no heteroclinic intersections can be present, and vice versa. If only homoclinic intersections of manifolds are present, it means that the transport barrier is there. So the lower picture shows the case when the transport barrier is broken, and there are heteroclinic intersections of manifolds in this case, except this could be turned vice versa. If there are heteroclinic intersections, it means that no transport barrier is present. I think it can be applied to multi-gyre systems. So, for example, if you have a more complicated, not 3-gyre geometry, but 10-gyre, 11-gyre, any number of gyres, this should be generally true. Non-local transport is governed by heteroclinic intersections.
I think we should thank the speaker, and thank you very much.